Good day, ladies and gentlemen. Today we have this question. It's draw the shear force and bending moment diagrams for the beam and loading shown and determine the maximum normal stress due to the bending. This is the problem, and as you can see there's two external members, FA and FB, and a distributed load, and we need to get a shear force and a bending moment diagram for those. Now before we do that, we need to calculate the external force members. We do that by using moment about A, and if you've done statics before, moment about A that means it's 0. Then we go 45 multiplied by the distribution across 2.4, and then multiplied by 1.2, because that one as a single force member, that will be in the middle of that. And then FB will be multiplied by 3.6, which is just the addition of 2.4 and 1.2. And then also, since we've defined the moment is positive clockwise, our 16 here is added as a positive, giving us 40.44 kilonewtons as a result. Then finding out force member A. Force member A minus the distributed load, which is 45 times 2.4. It's in the negative direction, so it's negative, plus what we just found for FB, which is 40.44. And as you can see, we found force member A to be equal to 67.56 kilonewton. Now, before we proceed, I would like to point out that for the last part of that question, the max normal stress formula, max normal stress sigma m equals moment max, which we will find once we have found our moments, and also the section modulus S, which is calculated by 1/6 base times height squared. Now let's get into the later details of that. So first, in order for our shear force diagram to be drawn, we need to find our shear force members from the left to the right. This is just the direction I've chosen to take. You can obviously go from right to left. Anyway, the shear force member, this is just a section. So the way you figure out the shear force member is that you cut the beam before just slightly past A, and then you do a sum of forces, so for Y. So we have that force 67.56 kilonewtons minus the shear force at A, equilibrium, so it's equal to 0. So shear force at A will equal to 67.56. Now, since this is a positive value, we would put it up there, so that will be in the positive. Next, we will find the shear force at C, and the way we do that is we cut the section just a smidget after C, and we have that same force, 67.56. We have the distributed load through the 2.4 meters, and then we have the shear force C. So we do exactly the same thing. Sum of forces in the y direction, 67.56 minus 45.24 minus the shear force at FC. equals to 0. Now shear force at FC will come out to be around negative 40.44 kilonewtons. Now when it calculates to negative 0.4, so shear force C will be negative 40.44 kilonewtons, and that's where the distributed load will end and will continue because there's no other external forces acting on that. Now, when we calculated SFA and SFC, we identified that there's an X here from A to D, where the line crosses over the axis and goes from the positive to the negative. So we need to find that X because it'll be crucial for us to identify the moments in order to draw the moment diagram. So the way we do that is balancing of the triangles. So we have the 67.56. That's the upper component multiplied by divided by X, which is that component, and then we equate that to the whole triangle, which is 67.56 plus 40.44, because that's the whole triangle, divided by the whole length, which is 2.4, and you'll find that X equals to 1.5. Now, finding moments from once we achieve this graph is easy because it's just figuring out the area in each section. So moment at AD is simply 67.56 in the positive multiplied by that length X divided by 2 because it's a triangle, and that'll give us a positive 50.67 kilonewtons per meter. A moment from D to C, that'll be in the negative quadrant, and we identified that SFC is negative 40.44. We multiply by the remainder from when you minus the 2.4 from the X, that'll be 0.9, and divided by 2 because it's also a triangle, and you'll get a negative 18.2 kilonewtons. And then MCB, C to B, you will have that same value here, the negative 40.44, and multiplied by that length. And then you also, don't forget, you also add the positive moment, and you'll get negative 32.53. So then if you were to draw the moment diagram, you look at the shear force, and on the shear force, if it is going up on the triangle, that means the slope is going up. And then so as it's going up, you have a slope, and at that point D, you will actually find that's the maximum moment. And then from that 50, you minus the 18.2, and that will go down to something approximately 32.53. And then from that 32.53, you minus the 32.53, which will stop there, but then because of that moment, it will come back and touch B. And in the moment diagram, the sum of moments equals to 0, so you always have to, when you start at on the axis, you finish on the axis. Now we need to find the max normal stress in order to complete the last part of that question. And as we identified the max moment as per that formula, equals to 50,670 Newton meters. And then the section modulus is, we get 7.81 times 10 to the negative 4 meters cubed. And when we put into that simple formula, we get 64.86 megapascals. Thank you.